Greetings, physics students. I wanted to take a few minutes and go over the circular motion part 1, torque and rotational equilibrium problems. The basic equation is right here. We use tau for torque. Tau equals force times distance. So torque is really a force that's applied some distance from a fulcrum or an axle, let's say, and sets up a twisting motion or a rotational motion. So since it's force times distance, torque has units of pound-feet in US system. We sometimes say foot-pounds. And in the metric system, Newton-meters. Now as far as signage, if the turning is in the clockwise direction, torque carries a negative sign. If it's in the counterclockwise direction, torque carries a positive sign. In problem 1, we're given the weight of the boy and the distance he is sitting out from the fulcrum. We're given the distance that the girl is sitting out, and we need to calculate the weight of the girl in newtons for there to be rotational equilibrium. In other words, for the seesaw to be stationary, to be balanced. And so for that, we just set tau equal to 0. And so in other words, the torque that is set up by the boy has to equal the torque that is set up by the girl for there to be equilibrium. So what is the moment arm for the boy? We're given the weight of the boy and the distance that the boy is sitting out, and we set that equal to the weight of the girl times the distance for the girl, and we solve it like that. So we're sort of treating it like two levers. The boy has a lever arm, force times distance for him. The girl has the same thing for her. And so it's a simple algebra problem. And just to give you a self-check, you'll come up with an answer between 250 and 300 newtons for the girl's weight. In question 2, this is a very practical problem in that with any mechanical device, such as an engine, every single nut and bolt will have a torque specification by the manufacturer. So this is telling you that the head bolts have to be tightened to 70 pound-feet of torque. So a manufacturer will do that because if these nuts holding on the head, this is the head right here, are too tight, they could fracture the part. If they're too loose, the part could come loose. So you'll see this with any engine or any mechanical device. Your basic equation would look like this, and it's set equal to 70 pound-feet. The force is what you're trying to solve for, and the distance is the length of the handle, in this case 18 inches, and you'll need to convert that into feet. That's 1.5 feet. So again, a very, very simple problem there. You'll get between 40 and 50 pounds, which is the necessary force. See, the wrench is there, the handle of the wrench, let's say, goes out to here. So the person has to push with somewhere between 40 and 50 pounds in order to achieve 70 pound-feet of torque in that case. Part B, just use a longer wrench, 24 inches. Again, you'll need to convert that into feet, which you know is 2 feet. You'll use the same equation. You'll just have a different distance. And as you might have guessed, the person doesn't have to push as hard with a longer wrench handle. So you'll get an answer between about 30 and 40 pounds for part B. He doesn't have to push as hard because he has more leverage, a longer wrench handle, to achieve the same amount of torque. Here we have two people carrying a load of bricks on a plank 2 meters long, about 6 feet long. So the free body diagram looks like this. We're calling this point A down here. This person is pushing up with a force of 400 newtons, which is given in the problem. Then we go to point B, and that force represents the load itself, this load of bricks. And then this person is carrying a little bit more. We're calling this point C, 600 newtons. So we use what's called translational equilibrium to solve for the unknown force, force sub B. And translational equilibrium just says that the sum of the forces in the y direction, the up-down direction, have to be 0 for there to be equilibrium. Otherwise, the plank would be, going up into the air or falling down towards the center of the earth, and it's not. They're able to carry it It's stable, it's stationary, everything is working. So we can say that the sum of the forces in the y direction are 0. So ask yourself, what are the forces in the y direction? Well, we have a negative 400 newtons down at the left end. We're calling any force pointed up negative and any force pointed down positive, just to keep our signage straight. So I'll put a negative sign there and a negative sign there. Then we go to the next one, which is the load itself, which is F sub B. And then we go down to the far right end, and we have a negative 600 newtons. And we set all that equal to 0 and solve for FB. So it's a pretty easy algebra problem. You'll get 1,000 newtons. The load of the brick, the weight of the bricks is exactly 1,000 newtons in this case. Part B gets a little more tricky. Exactly where along the plank are the bricks centered? Because they're not in the middle, you know that, because the person over at point C is shouldering more of the load. To solve this problem, we're going to use a concept called rotational equilibrium, and we just simply set the sum of the moments around point A equal to 0. You're saying moment, moment. What does moment mean? In physics, we actually use the term torque. In engineering, we use the term moment. It's the same thing. It's a twisting force. It's force times distance. So I'll switch my terminology over to torque for you physics students. And we know that torque is simply force times distance. So what we're doing in essence, let me change colors really quick here, keep things straight. We're taking point A and calling it the fulcrum, and we're making this into a hinge. We're pretending the plank is a hinge and the fulcrum is down at A. And we're going to take each of the forces acting on that quote-unquote hinge, add them up, and set the total equal to 0. Why can we do that? Because the plank isn't spinning around in the air, so they have to be 0 for there to be equilibrium. So very simply, just start at point A. What is the first force that we come to? We've come to force sub A, F sub A, which is 400 newtons. So let's just for now write FA, and the distance from point A is 0 meters. So that term is going to zero out, but we want to include it anyway for consistency. Let's go to the next force that's acting on the plank coming out from point A. That would be FB. So we want to put that times its distance from point A, which happens to be the amount we're trying to solve for. So I just put an X in the drawing up there. So our unknown we'll call X. Now, is that going to be a positive torque or a negative torque? Ask yourself, force B, which is pushing down, is it trying to rotate the hinge clockwise or counterclockwise around fulcrum A? Well, if it had its way, it would like to rotate that plank slash hinge clockwise, assuming A is our fulcrum of the hinge. And clockwise torque is always negative, so we'll put a minus sign in there. Now go out to the third and last force. It's force sub C, which is on the end, which we know the amount. We'll substitute it in the next step. Now what's the distance? The distance is given up here. It's 2 meters. That's sitting 2 meters from point A. Point A is always our reference point here. Now do we put a plus or a minus sign out in front? Well, ask yourself, is force C, which is pushing up 600 newtons, attempting to rotate the hinge contraption counterclockwise? Yes, it would like to rotate it counterclockwise. It's not doing so because everything is in equilibrium. But if it could, it would rotate the hinge, the plank, counterclockwise around point A, assuming point A was the axle. And any counterclockwise torque has a plus sign. And we take that whole thing and we set it equal to 0. Next step is just substituting. FA times 0 is 0, so that term goes away in essence. Force B, in other words, the load we solved in part A at 1,000 newtons. So write 1,000. X is what we're trying to solve for. And then substitute in 600 newtons for F sub C, and it's 2 meters out, equals 0. And now rearrange. I'm sort of running out of room, but I slipped in the next line right there. We have 1200 equals 1000x. So now we're getting really close. So you know that you divide both sides by 1000 in order to solve for x, this distance right here. And that's how you do the problem. So I don't think you need a hint, but just in case you do, it's between 1 and 1.5 meters from the left end of the plank. So that's how you would answer part B. This is kind of an interesting biomechanics problem. So step 1 is to come up with a decent sketch that models what's going on. The person is trying to curl a dumbbell, 7.5 kilogram. It's giving us the length of their forearm, and it's giving us the distance that the biceps muscle attaches from the elbow joint. So we're looking at this picture. Now the problem is being simplified a little bit in that the angle of the forearm we're supposed to assume is 0 degrees to the horizontal. So the picture says 40 degrees here, and we're assuming that that is 0 degrees. It just makes the problem a little bit easier. So step 1 is the free body diagram. It would look something like this. We need to figure out what 7.5 kilograms is in terms of newtons. So F equals ma, of course, Newton's second law. So we'll call that the force exerted by the weight, F sub W. That's going to be ma. So the m is this, and the a would be that in metric units. Very simply, to solve this problem, we use rotational equilibrium again. So we set the sum of the moments, or for you physics students, the sum of the torque around elbow, so I'm saying tau sub E, equal to 0. In other words, the bicep muscle is creating a torque around the elbow, and it has a moment arm 5.5 centimeters long. And the weight hanging out here, the dumbbell, is setting up a moment or a torque around the elbow as well. We're treating the elbow as the fulcrum. And its moment arm is longer. It's 38 centimeters. So by setting the force times distance for each of those two forces equal to each other, we can solve the problem. In other words, we're setting the torque set up by the bicep muscle pulling on the forearm equal to the torque created by the weight, the dumbbell hanging out at the end. Since torque is force times distance, the basic equation looks like this, and we're trying to solve for F sub B, the force that the bicep muscle has to exert on the forearm in order to hold up the weight. So the distance here for the bicep is given. It's 5.5 centimeters, and you don't even have to convert it into meters if you don't want to, because the distance over here, the distance of the dumbbell, the distance of the weight, is also going to be in centimeters. So you can leave those in centimeters. The centimeter units will cancel out. Makes it a little easier. So you'll put 5.5 in for this. For this distance, you'll put 38. And for this force of the weight of the dumbbell, you're going to put in 73.5 newtons, and you're going to solve for the force required to be exerted by the bicep muscle. And just to give you a rough approximation, it's going to be in the neighborhood of 500 to 600 newtons. But I do want to see all your work, of course. Part B here does it in US units. So now you're trying to curl a 50-pound dumbbell, which is a pretty heavy dumbbell, and calculate the minimum tension in pounds needed by the biceps muscle. In that case, you'll use the same exact setup, and you'll find that the bicep muscle has to exert a very strong force between 300 and 400 pounds just to curl that 50-pound dumbbell weight. So that's pretty surprising how much force your bicep muscle actually exerts on your forearm. This is a biomechanics problem on the foot now. You do have to make some assumptions. I would draw the free body diagram like this, with the foot being the horizontal line, the ankle being the fulcrum, and FT up here is the force exerted by the tendon, 4.5 centimeters out, and 16 centimeters going the other way. You would have the reaction force of the ground, F sub G, pushing back on the toes, or the ball of the foot right there. Now the problem states that the person weighs 800 newtons, so that would be this force here, because you have to assume that the person isn't running or sprinting or jogging down the sidewalk. They're actually just standing still. So we'll assume that the force, reaction force that the ground is pushing back, is exactly their weight. And it's asking what force in newtons must the Achilles tendon exert. We're calling that F sub T. And it says ignore the 30 degrees in the picture. So we're making the problem a little simpler by ignoring this angle. So again, this is a rotational equilibrium problem where we just set up the torque tendon equal to the torque exerted by the ground, and torque is just force times distance. So we set this FD equal to this FD. That force right there would be the unknown. That's what we're trying to solve for, F sub T. That distance right there would be the distance from the fulcrum right here. It's given in the problem, 4.5 centimeters. This force over here would be the 800 newtons, and this distance here would be this distance out here. So it's a real simple algebra problem at that point. You get an answer between, let's say, 2,500 and 3,000 newtons, which is a lot of force. It's pretty close to 700 pounds. So if you think about a person that weighs 800 newtons, which is about 80 kilograms, which might be close to 200 pounds. The tendon, Achilles tendon, is exerting a force probably around 700 pounds, just holding that person on the ball of their foot. So it's kind of amazing. This is an old-fashioned mobile, which you may have seen. This would be a classic problem on physics exams, and it's very simple. You just, number one hint, work up from the bottom. You have to work up from the bottom. So you come down here and it's saying find the weight in newtons of balls A, B, and C. So you start at the bottom. You start with this one right here. And you just set force times distance over here equal to force times distance over here. It's rotational equilibrium. It's like a seesaw, basically. And this point S3, this point right here, is your fulcrum. So you have 6 times 4, okay, has to equal 8 times A. It's pretty simple. You'll find that A, let's see, I'll give that to you to get you started. That's 3 newtons. Then once you have that, you can go to the next level, ball B, because now you know the weight down here. It's not 3 newtons, it's 6 newtons plus 3 newtons, which is 9. So now you can go up to the next level. You know that that's going to be 9 newtons right there. And you do force times distance here, has to equal force times distance here, and you solve for the weight of ball B. Then you move up to ball C, and in order to use the right weight down here at the left end, you have to add 9 newtons to the weight that you just calculated for ball B. Don't just use 9. Don't forget to add both of them, and that gives you the total weight here. And then you just do FD equals FD, and you get the weight for ball C. So let's see if I can give you some hints here. For ball B, you're going to get between 10 and 20 newtons. For ball C, you'll get between 5 and 10 newtons. Then part B is find the tensions S1, S2, and S3 in the strings. Well, you basically already did that, because look down here at S3. Let me change colors here, keep from getting messed up. S3 is right there at string 3. The tension in string 3 is just going to be 6 plus 3, 9 newtons. And you just work your way up from there. The tension in string 2, I'll give you a hint, it's between 20 and 30 newtons. The tension in string 1 up here is between 30 and 40 newtons. But I do want to see all your work on that, of course. So that's it for this assignment. Let me know if you have any questions.